Okay, everyone, we're very happy to have the Kadnov seminars starting again. So today we're doing a bit of an in-person introduction to some of our new postdocs. So Subham's going to be talking about some past work. Yeah, Subham, take it away. Thanks so much.
Thank you. Thanks everyone for joining in. So today I'll be talking about some work that I did last year with some collaborators on bounds on flat space scattering from some CFD theorems. So this is based on this work which came out last year and also some ongoing work with these collaborators. So let me try to first set up what sort of
There's
bounds.
some feedback. Edward, can you mute yourself?
Yeah, sure.
Or the theory group, or somehow I think the fact that it's broadcasting through and then coming into the mic is creating some feedback.
We've never had this issue before. People won't hear you. Yeah.
It could also be that Subham was on twice. Could he have
the microphone? One second. Let me just check.
No one will be able to ask questions here.
Yeah, maybe Subham, is one of your devices?
Yeah, it's muted because I have not joined via audio for this device.
Now it sounds better now.
Now it sounds better.
Somehow, yeah.
Okay. If there's any more issues, Clay, just let me know and I'll mute it.
Yeah. Okay. So let me set up some background regarding as to what sort of bounds I'm talking about. Usually we're familiar with the Frossa bound. Let me explain what that is. So suppose that we have a UV complete QFT with a tunable coupling constant and a mass cap. That's mass cap is important. Then the 4-point scattering amplitude for such a theory obeys what is known as the Frossa bound. So if you look at the cross section for such a scattering amplitude, and in the largest fixed behavior of the cross section is given by this sort of a behavior, where you see the mass cap featuring in the bound. Since this was a full quantum theory, UV complete QFT, let us consider another parametric limit of this theory where we tune the coupling constant to 0. And we study the same kinematic limit of the leading term of the expansion. What I mean is that I'm looking at energies which are far lesser than 1 over G. So therefore, we don't probe loops in the theory.
Sorry, so what is G?
Sorry?
What is G? G is a coupling constant?
Yeah. Some coupling constant.
So we're imagining a family of theories that can be tuned to weak coupling?
Yeah.
When we're making these statements?
Yeah.
Okay.
Yeah. And
this equation doesn't make sense dimensionally. What do you mean by S is less than 1 over G? S is dimensionful.
What I mean is that I'm probing energies which are far less than, say, maybe I can write a better this thing that S is, let's say that does that make sense?
But what does that say? The Planck mass? What does the Planck mass have to do with weak coupling? This is some QFT.
Yeah. So what I'm saying is that I'm not looking at energies where loops become important. Yeah.
But that's an energetic statement?
Yeah, right. I mean,
well then how do you say it in a QFT? It shouldn't have any reference to the Planck mass since we're not
talking about the power of the gap somewhere to make the dimensions work.
Okay. Just 1 second. Okay. Maybe this is not a good way of saying it.
Supersymmetric.
Sorry, what's wrong with just sprinkling MUV with G until it becomes unitless? Or
what is MUV?
Well, he's dealing with a theory that has a mass gap.
Yeah.
In the UV.
So okay, so you think it should be S is less than MUV?
Some M.
I mean,
Maybe
he just wants, I
M
guess,
squared.
like he says he wants to suppress the loops.
Yeah.
Write a loop scattering diagram and see what the suppression factor is.
Well, that's what I'm asking.
Yeah.
But is that actually correct? Like, in particular, that would suggest that in a theory without a mass gap, loops are always important.
No.
I don't think that's actually true. Like,
No. So what do I mean by this? Okay, maybe in the next slide, maybe I can actually say something more concrete, like this thing. Okay, so what I'm trying to say is that I'm just describing the setup for say classical scattering, which is basically we will just consider amplitudes which are just simple poles and analytic pieces. We won't have loops. Yeah. Suppose that we consider massless theories in this regime, and to be more specific, like we have the energy range which is defined by this. Does this make sense? Like,
usually S has dimension 2.
yeah. So sorry. I mean, I'll just say
4 dimensions. Yeah.
Sure, sorry.
something like that.
Yeah. Okay.
So basically, like my setup will be something like this, that I'm trying to probe a say weakly coupled string theory, which is the similar kind of setup which was probed by considered by Kameno, Edelstein, Maldacen, and Zhibodev, where you have corrections to Einstein gravity, but you don't have gravity loops in your amplitude. So that's the setup that we are looking at. And I'm asking, like, can we put bounds on the S matrices in this classical regime, where you just have poles and analytic pieces in your scattering amplitude?
Sorry, so didn't you say that your field theory is UV complete?
No. That was for Frossa bound. We know that for Frossa bound is like for theories with a mass gap. I'm saying that I'm trying to say that can we say something similar for theories which don't have a mass gap? And I'm just describing the setup for those kind of theories.
Okay, so then you must be dealing with a field theory in which precision of calculation is intrinsically tied to the energy scale, which is the case when you have some sort of higher dimensional operators. Then precision of observable is tied to the energy scale. I don't know if that's what you are talking about. I mean, in UV complete theory, the statement doesn't quite make sense to me.
Yeah, I'm talking about say theories such as like you have Einstein-Hilbert action, and like you add like a number of higher derivative terms to it. That sort of a theory.
Okay.
That is the regime in which I'm working. I'm not saying that this is like full UV complete theory.
when you say bounds on S matrices, you're talking about a la the Frossard bound, like some scattering amplitude doesn't grow.
Yes. Are there any more questions about the setup? Okay. So in a series of previous works, what we postulated is that we postulated something called the Classical Regge Growth conjecture, which was that the S matrix. So this was a consistency condition that we postulated, that the S matrix of a consistent classical theory never grows faster than S square at fixed t at all physical values of momenta and all for every possible choice of normalized polarization vectors. Okay, and it led to very surprising constraints on modifications to Einstein-Hilbert action. We found that for if you are looking at dimensions less than 6, no finite number of Riemann polynomial corrections can be added to Einstein gravity, fourth order Riemann polynomial corrections. Okay, and this analysis was very similar in spirit to constraining 3-point couplings by Kamenov, Elstein, Massless, and Ashibadev, but as we'll see that it is a bit different physics.
Can you remind us, if we if we remove the word classical from the first bullet point, then it's just supposed to be true, right? That the full amplitude is supposed to not grow faster than S squared at fixed t.
So this classical Regge growth conjecture says that it can also be S squared, whereas the Froissart bound or equivalent to Froissart bound for massless theories say that like it must be strictly less than S squared. It cannot ever saturate S squared. So I'm saying that like it has to be less than equal to S squared.
But it's almost like you're saying that there's a sign to loops, like loops can't lower the exponent too much. Like the classical scattering that you're talking about, it's just some particular particular leading term.
Yeah.
Right, and you're saying that the loops can't change the exponent. Am I interpreting it correctly?
I think that for massless theories, like there is no like equivalent statement about like Froissart bound, but like the way I will present the derivation of CRG or this classical Regge growth conjecture from CFT principles, you will see that like the idea is that the full quantum theory, it cannot grow faster than S, not S squared. So it's just not like it, including quantum corrections. I don't think like it just says that, okay, something, some amplitude which was growing like less than equal to S square now should be like strictly less than S square or something like that. I think it is now becoming something less than S. But there is no proof of this, of course. Like, I mean, I'm just saying that like for massless theories, there is no analog of Froissart bound. So in some sense, this is.
And can you also clarify fourth, you mean like there's no R to the fourth term possible for Einstein gravity? Is that what you're, as a correction to Einstein gravity?
Finite number of R to the power 4 terms. But of course, we know that like, if you consider, for example, string theory, which all has an infinite number of such corrections. So infinite number of such corrections, we can't say anything. Like, I mean, it's either like, we are just saying that there are no finite number of Riemann polynomial, fourth order Riemann polynomial corrections. Like, but
it sounds a very unnatural thing. It's not normalizable. Why would it ever be a finite number? Like, wouldn't you always need more counter terms and therefore
sure, but I'm looking at classical scattering. I'm not even
but the classical scattering is just some piece of a quantum mechanical EFT.
Right? I think it's a way to make this naturalness idea sharp, maybe in this context. You can show that indeed you need these extra terms.
Yeah, it's kind of like, I mean, showing that like there is something wrong if you like, you know, even at the level of classical physics, like if you consider just this thing, even if you don't think about renormalization and stuff like that. of course, like, I mean, if you have an infinite number of higher derivative corrections, you're fine, like, because that's an EFT and you would always this thing. But as a classical theory where the correction, the coefficient in front of the corrections are of order 1, this is inconsistent. That's what we are trying to say.
Can you say what kind of inconsistencies do you expect if this classical Regge growth conjecture doesn't hold for a given theory?
Yeah, like, so in the present context, we show that, like, if you think of this flat space scattering as like as being derived from flat space limit of an ADS theory, that ADS theory is inconsistent in the from CFT principles. It violates something called chaos bound. That's how we prove. That's how we define this consistency condition, at least in this thing. But of course, a pure flat space notion of what consistency means in this case is we have not. It's still an open question, like this thing.
Maybe a more specific question, like, so I set up some initial data, I throw in some incoming stuff.
Yeah.
What happens if I'm an observer at late times. What do I see?
Yeah, we have not explored that. That is one of the ways we are thinking, like, one should look at it now. We have not looked at it in that thing, like, the usual, like, initial value problem kind of things.
Right. Yeah. So there might be a connection with, like, just well-posedness of the equation.
Yeah.
Okay.
For sure. Okay. All right. So, of course, as you all pointed out, like, why would you expect such a thing to happen? Like, what is the why would you expect this? So there are 3 main evidences for CRG. First is that, like, most well-known, like, two derivative field theories that we know of, they satisfy CRG. Like, it's kind of like an example-based evidence that, like, we know that theories and also one of the most striking thing is that, like, Einstein gravity actually saturates CRG. Like, so for example, if you look at tree-level tree-level scattering in Einstein gravity, you will find that the graviton exchange diagram that grows like a square over t with some, like, like polarization vectors hanging around, which I have ignored. It saturates CRG. And tree-level string theory is even better. Like, it's strictly less than a square. Like, it is because the tree-level Virasoro-Shapiro amplitude grows like s to the power 2 plus alpha prime t, where t is less than 0 for physical this thing. Okay. Then we have more evidence for this thing to hold true from the seminal paper by CEMZ. I'll be very brief in explaining, like, this thing. So the main crux of the argument, like, where we've thought that, like, it can perhaps lead to CRG type bounds, is given in a neat little appendix, I think appendix D of their paper, where they try to interpret this scattering experiment as sort of a signal propagation model. So so in this paper, what they do is that like they try to set up this causality problem where they are trying to probe the time to evaluate the time delay of proof particle passing through the shock wave of another, and that is related to the iconal scattering of gravitons. Okay, and this signal process, this scattering process, you can think of as a signal propagation model involving exciting the gravitons 2 and 4 across the shock wave created by gravitons 1 and 3. Okay.
Subham, quick question.
Yeah.
Is it right that this iconal regime actually sums up like infinitely many ladder diagrams? So are there actually loops here that we're
but this is still classical. Like this is still classical scattering. You it's also it's like I mean, you can compute this iconal scattering just from a classical shock wave calculation, like time delay across a shock wave. Okay, so somehow this is like still a classical thing. It's not quantum. Like you don't have, it's not quantum loops. Yeah.
What's the difference between a loop and a ladder?
Thanks.
I mean, I guess it would be that you would have log s kind of terms like in your amplitude, log s, s log s kind of terms, logarithmic divergences in your amplitude. Those would be the signature of like loops, I would suppose.
He's not doing iconalization. He's just looking at classical tree-level scattering.
In a background.
No background. I mean, the CAMS calculation did two calculations. One was to have a background which was a shock wave and show that there's a Shapiro time delay.
Yeah.
That might be what he's describing. Another way to see the same thing
but
is...
that I wouldn't call fully classical.
Yeah. What about a iconal limit of a scattering amplitude?
Yeah, I think like, I think these two are the, like this pro particle, like the time delay across a shock wave. I mean, this is the same as the iconal scattering of gravitons. This Daniel Kabat and Ortin, like I think showed this.
Finite T large S.
We can figure that out later. Thanks for.
Yeah.
Yeah. So basically, like their analysis was that like you map this scattering process into a signal model where you just look at the signals which you think of the signals as exciting the gravitons 2 and 4 across the shock wave, and using causality and unitarity, you would they show that the ratio of these incoming and outgoing signals must be bounded, like and to be precise, the S matrix of in impact parameter space for such a scattering must be bounded, like it must be bounded. And in terms of the tree level S matrix in impact parameter space, you can show that, like, I mean, this translates to this inequality. And if you assume that your impact parameter space S matrix S grows like this, one can show that this implies this exponent of S, which is given by A delta, this must be less than equal to 2. So roughly, perhaps one can say that the fact that this impact parameter space S matrix obeys CRG implies that the position space S matrix also, like momentum space S matrix also obeys CRG. but this would be a bit fast in the sense that we kind of assume that the transition from momentum space to impact parameter space is kind of smooth, and that and also because this won't be applicable if the S matrix is generated by contact terms, because those are analytic in T, and therefore like the impact parameter representation is a bit tricky. Like, I mean, it's essentially a Fourier transform. So like you will have divergences to deal with. So, so while this was very promising, it did not tell us that the S matrix should be actually be bounded by S square. The third piece of evidence, and which we will expand upon, is that is something called chaos bound. So what chaos bound states is that, like, if you look at like theories which have parametric separation in scales between dissipation time and scrambling time, such as holographic systems, the out of time ordered correlators in such systems cannot grow faster than a given rate. Okay, and that is called the chaos bound. And as we will see, that this implies constraints on time ordered Minkowski correlators in CFT. And using the relation between holographic correlators and flat space limit of ADS CFT, it seemed to us that some version of this statement must be true, and that's what we have made precise in this. And we must say, I must say that like many others seem to have suggested this, like we are not suggesting it for the first time, and like it's well known, we just made it a bit more precise. Okay. So let me just outline, since there are many moving parts in the system, like let me just give a broad outline of how I will show this thing. So we will first consider a class of holographic correlators, that is, we'll look at large and strong coupling CFT correlators, which are generated by bulk contact terms. And since these are conformal correlators, they are functions of two cross ratios. We will study two Lorentzian regimes of these correlators, which we will define in a moment, which are called causally Regge.
Where is the weak coupling in the CFT? I'm missing that. So I thought your discussion was about some one parameter family of theories that can become weakly coupled.
The CFT is not weakly coupled. The flat space, the KFT, which you get in the flat space limit, that is weakly coupled, right?
So you don't have a one parameter family of CFTs?
No. It's like we are looking at like holographic CFTs. Like
here it's large N, right? That's basically doing that.
Large N as well as strong coupling. We need that.
No, but is N playing the role? Is 1 over N playing the role of G? Is my question. You had some discussion previously about some G to 0 limit of scattering amplitudes.
Mm-hmm.
And the claim is that they have some property. I'm asking, what is G?
From the CFT perspective,
it's suppressing his loops, so it's probably
I think like we are looking at the semi-classical bulk, right? I mean, so yeah, I suppose that is what we are what you are saying. Yeah. So we are looking at like the leading behavior only, like not like subleading, like yeah. So we will study two Lorentzian regimes of these correlators, which are called these are generally called causally Regge and causally scattering. And we will also study two kinematic limits of interest. One is called the Regge limit, where one of these cross ratios go to 0 while the other is held fixed. And we will show that the class of contact terms that we consider, they have in this Regge limit, they have a behavior like this, where G, this is some function of rho, and this is some and it has a singularity in sigma and this power A prime depends on like the type of interactions that we are looking at. We will show that this can be so we will obtain these results on this one Lorentzian regime called the causally Regge. We will show that you can actually analytically continue to this causally scattering sheet, and this exponent doesn't change. And then when you tune the other cross ratio also to 0, you have a singularity in both sigma and rho of this form. Okay. The other and like the importance of this regime is that like this is the regime where chaos bound applies, where these correlators on this sheet, like they are constrained by chaos bound, and yeah, and we will be very, I mean, it's very crucial that we will be making use of this very crucially.
Which of these variables is S?
Sorry?
Which of these variables is going to become S?
So the sigma will become T over S.
And rho?
Rho will not have any analog in in terms of Mandelstam invariance, but like the exponent of rho will be determining like what derivative order interaction you're looking at. So sigma basically like it leads, it's of the order sine square theta by 2. Like roughly you will see that like that comes about.
So we want to prove that A and A prime are small.
Yeah, they are bounded like this.
See, sorry.
Yeah. And I mean, one can ask like, I mean, why, how do you know that this is related to scattering? And and it becomes evident that this is related to actual flat space scattering in this something called the bulk point limit, where you look at the other order of taking the limits, where you take first rho to 0, keeping sigma fixed. And this is known in literature that that if you take a holographic correlator and apply this limit, and you will get something like this, like for bulk contact terms, and this coefficient, like will be your flat spaces matrix. Okay, this will be a function of T over S, and like you will also have like some powers of momenta sitting outside, and this will give you like your flat spaces matrix. So we want to show that like in these two different orders of taking limits, where sigma goes to 0, rho goes to 0, they kind of commute, and like you have this object, and using the chaos bound, which puts bounds on this, you will say that like we will say that this this happens. Okay, so this is the general structure of the argument. And if there are any questions, like probably, yeah, I can take them at this stage before moving on to details.
Versus what you're going to input. So you have a holographic CFT, and you're assuming that its correlators are going to come only from bulk contact term scattering? Is that part of the assumptions?
Yeah, we are only looking at, like, suppose that you are looking at, we want to study like the flat space scattering, analytic pieces in flat space scattering. We are not looking at, say, exchanges. They can only be generated by bulk contact terms.
But what is the role of the CFT? Then why introduce the CFT at all?
Right. So CFT provides me chaos bound, because we know that chaos bound applies to holographic, at least for, like, for, it's a CFT theorem, right? So it doesn't have any implications for flat space CFT as it stands. So we have to impose the constraints on flat space scattering via flat space limit of ADS CFT.
Do you agree that not all S matrices can be obtained from a flat space limit?
Yeah. So, like,
CFT
it's
is just buying you like a Froissart bound.
yes. Well,
or a massless theory.
yeah. I mean, massless analog of Froissart bound. Yeah.
But is that something I'm supposed to believe holds for every S matrix? I mean, is that like I'm kind of confused about how I'm supposed to take the answer to Nima's question.
Right.
Like, am I supposed to think that this is some just extra restriction we're putting on our S matrices, or is this something that you hope someday you could prove about all flat space S matrices?
Yes, that is this. Whatever you said for the second one, like, is the hope. For that, you need to prove like this boundedness of your S matrix directly in flat space, not use ADS CFT. Maybe some recent developments in S matrix bootstrap can help us in doing that, but as of now, this is the best that we were able to do. Like, at least for a subset of such theories, we can show that indeed it will be bounded, like, by this thing.
So what's like, talking directly about the bulk theory? The problem is that on one hand you want to do a classical thing, but on the other hand the chaos bound applies to some quantum theory.
Yeah,
that's the issue. That's why you couldn't do it directly in the bulk, so to say.
Right. I mean, the bulk, there is no notion of scattering in ADS bulk, right? I mean, you don't have S matrices.
Well, in flat space.
Like, I mean, that the thing is that you have to take the flat space limit. I mean, it's a kinematic limit. We must ensure that, like, the whatever which translates to growth of S matrices in the flat space limit does not change because of this taking the flat space limit.
Maybe let me ask the question this way. If I take the H bar goes to zero limit of the chaos bound, do I get anything?
No, it will just, I mean, it's, this is 1 over, and it's a quantum effect.
Okay, so the issue is that if I wanted to study pure classical GR scattering in flat space, I wouldn't be able to use the chaos bound, because that one I have nothing.
Okay. We don't have any. I don't know of any, like.
But if the I guess I'm still sorry for the confusion, but if the chaos bound trivializes when H bar goes to 0, why does it help you in this problem?
Yeah. That's basically my question a little.
The chaos bound on the boundary.
Yeah, the chaos bound is on the boundary, while we are looking at flat space S matrices of 1 higher dimension, I guess. Like, so this thing is not so, like, I mean, I don't think like it's so trivial in the sense that, like, you can relate the H bar goes to 0 limit of the chaos bound to the flat space scattering, right? I mean, this is the CFTD theorem in CFTD is putting constraints on flat space scattering in D+1 dimension. Like,
thanks. I was just basically asking, like, if there was a way around having the crutch of the CFT along with what Clay was saying, but it seems that it's to have some sort of well-defined quantum system. But
Yeah.
I am still also confused as to why the classical limit still yields some sort of bound, but we can talk about it later.
We are not taking the classical limit of like the CFT, right? We are not taking the classical limit of the CFT per se, right?
Well, you're maybe taking the only such classical
N goes
limit
to
that it
infinity.
has. Yeah, n goes to infinity is maybe the only classical limit that it
Yeah.
has.
That's what I meant. Yeah. So
The chaos bound is fine at 1 over at large n.
does it say anything at infinite
It
n? or-
saturates, I think, at large n.
Sorry, what?
The chaos bound saturates at large n, it doesn't go away.
Yeah, Edward, I think
Yeah.
part of the confusion is on my part is just what Shubham just answered, which is that H bar and the CFT is, or if you like, the classical limit in the CFT is not the same thing as the classical limit in the bulk scattering.
Yeah. Great. Yeah. Thanks.
Okay. Okay. How am I? Oh man. How am I doing with regard to time? Like with respect to time, how much?
You have 10 minutes.
We can
That's why
just
we don't
end
let
it here
Clay
and
organize
ask
the
questions.
seminars. I mean, we started like 10 minutes past. So you've got at least 20 minutes, and I think there's a good 5-minute wiggle room. So.
Okay. But like, I mean, it's important that, like, I mean, if you understand, like, at least the flow of this argument, like that I described here, like, I think like the rest of it will be details, like how you flesh it out for contact terms. That's it. Like, but like, I mean, yeah. So if I am getting this slide across, like, I think like everybody should get something from this talk, like. Okay, so now I will move on to the details. So let me first describe the kinematics of the thing that we'll be looking at. So I'll be considering CFTs with insertion points, like 4-point functions of CFTs with insertion points on the ADS global ADS cylinder, where the insertion points are like this. Okay, and we will be working in embedding space formalism, which is like a D+2 dimensional formalism, like since the conformal group has natural action on light rays passing through the origin of RD, 2, a very efficient way of studying CFTs is to embed it in this higher dimensions and take sections of these null cones in the CFT, null cones, and that describes your operators in the CFT. So the boundary points of in embedding space formalism are given by that pi square must be 0. Well, bulk points are parameterized like this, that it must be -1. Okay. Now, so for a pictorial representation, that if you consider the ADS cylinder, you have 2 insertions here at time. The global time runs in the vertical direction, and you have 2 of the insertions like this, and the other 2 are kind of at the antipodal point of these 2, but like, you know, like somewhat like deflected by an angle theta. Okay, this theta will play the role of like the angle of scattering in our flat space CFT, flat space limit. Okay, and the conformal cross ratios are given by this. Okay, they are dependent on tau and theta. And as I said before, that we need to look at two causal configurations, and the causal relationships in the cylinder are determined by this object. Like, so you take two things in your 2 insertion points, and you compute this inner product, and if it's greater than 0, all the points are space-like. these are the causally Euclidean thing, like where all the operators are space-like separated from each other. And one can check that this appears, this happens when the tau parameter is greater than pi minus theta. Okay. Similarly, like you have the causally Regge configuration, where the two pairs of points are time-like related to each other, but these groups of points are space-like separated from each other. Okay. It's kind of like let me just try to see. So suppose that you have this, like the Regge configuration would be like operators like this, where they are time-like related, but as a whole they are space-like related. Okay, and then you have configuration for causally scattering region. Okay, and this is given by when two operators are like this. Okay, so two of them are in the past, in the future light cone of the other two. Okay, and for Regge scattering, for Regge causally Regge regime, the tau must be of the order like this, like tau must be greater than theta but less than pi minus theta, while for causally scattering, theta must be less than tau. Okay, one can easily check that using the formula, relevant formula. So now, as you like, starting from a Euclidean configuration, you can move your operators up and down to change your causal configurations, right? Because as you move up and down, like operators will come into the light cone of the other one guy. Now, as you cross each other's light cones, you will encounter singularities. So in order to avoid that, we need some I epsilon prescriptions, and the I epsilon prescriptions that we will use is given by this. Okay, tau will be shifted by minus I epsilon tau. Now, as we are varying tau, in the last slide you saw that we are like exploring various causal configurations, and it's interesting to see what this traces out in the complex ZZ bar plane. Okay, so as you move tau from greater than pi minus theta to less than theta, the path traced out by the complex Z in the complex ZZ bar plane is something like this. Like as you move from Euclidean to Regge configuration, Z bar rotates anti-clockwise about 1, while Z remains fixed in the upper half plane. While if you further lower theta, further lower tau, you go from Regge sheet to scattering sheet, and that involves the Z making an anti-clockwise rotation about 0. Okay, so these are the two important analytic continuations we'll be working with throughout our for this purpose. Okay, now let me describe the limits first, why we should study these limits. So in the limit, the Regge limit can be taken both on causally Regge sheet as well as causally scattering sheet. Okay, this is a kinematic limit, and I'll just describe how do you take the limit. So this limit is taken by you take theta to 0 and tau to 0, but keep the ratio fixed. Okay, in terms of cross ratios, it's given by this. Okay, you rotate 1 minus Z bar and 1 about anti-clockwise about 1, and then take Z and Z bar to 0 with the ratio held fixed. Okay, now why is this important? So in terms of operator insertions for in ordinary CFT, the Regge limit is that you take 4 operators. Okay, you have taken 4 operators this thing, and you have boosted 2 of them towards the light cone of the other 2. Okay, so this is the Regge limit for a usual CFT, and sorry, yeah, this is the usual limit for a CFT, is a Regge limit for a CFT correlator, and we want to like relate this to chaos bound. So how does that happen? Which is for a thermal CFT, by the way. So let us review briefly like what the chaos bound actually tells us. So if we consider the out of time ordered correlator in a thermal field theory, okay, the chaos bound says that like okay, this should have been T, but yeah, okay. Chaos bound tells us that the connected part of this correlator, which in angular quantization looks like this, cannot grow faster than e to the power t at large T. Okay, so so what I have done here is that like I have taken the thermal correlator with temperature T is equal to 1 over 2 pi. And that is equivalent to a Euclidean correlator in angular quantization. And like, you know, some of the operators have some imaginary part, some Lorentzian time. And the statement about chaos bound is that like as you tune the Lorentzian time to infinity, this connected part of the correlator cannot grow faster than e to the power t at large T. So more generally, this correlator has the normalized correlator has a structure like 1 minus 1 over n square e to the power lambda L T. Okay, so in units of if beta is 2 pi, it just says that lambda L must be less than equal to 1. Okay. That's all that this is saying. Now, how is this related to a Minkowski CFT? Well, I mean, you can consider the same correlator, but in Minkowski space on a Rindler wedge. Okay, and like the way to do this is that you make an analytic continuation. Tau Euclidean goes to I using this sort of a analytic continuation, and you get a Minkowskian correlator, like zero temperature Minkowski correlator on Rindler wedge. And it turns out that like if you do your algebra correctly, the OTOC in angular quantization becomes a time ordered Minkowski correlator on the Rindler wedge. And so the chaos bounds on OTOC translates to constraints on the Regge correlator, and like, I mean, I'm just stating here for future reference that if you it basically says that the Regge correlator cannot grow faster than 1 over sigma at small sigma. Okay, so that's how you get the chaos, I mean, how chaos bound translates to constraints on time ordered CFT correlators. Are there any questions at this stage? Because this might have been a bit fast, but like okay. So we have studied like what the Regge limit is useful for. The other limit is the bulk point limit, and it is taken usually on the causally scattering regime where two of the operators are in the light cones of the other two. And this limit is taken by like you have the rotation of z bar around 1 and anti-clockwise, and also you rotate your z about 0, and then take z goes to z bar. Okay. So why do we want to study this limit? So it happens that like as tau goes to 0, okay, the insertion points actually they don't remain no longer independent, and in fact they have like they behave like this. Like you can check that this behaves like this. Well, I mean to say that it's basically 2 tau times some vector which is identity. Okay, So basically, as tau tends to 0, you can think of this condition like as some sort of momentum conservation condition. Like you see, like you have P1, P2, P3, P4 to be 0. Momentum conservation is, we can think it will turn out to be the momentum conservation condition. Now, what happens is that, like for large N CFTs, a strong coupling in the causally scattering configuration, the correlators develop a singularity in the bulk point limit in tau. Okay, this was the result of Massless, Zhukodev, and Simon Stuffin in a very nice paper, and I mean, and it was I mean, assuming that all such holographic correlators will show such a singularity. In 2009, Gary Giddings and Penadona showed that this can be related to flat space S matrices. Okay, the coefficient of the singularity in conform correlators can be related to flat space S matrices. Okay, so let me just briefly say how this comes about. So so suppose that we have the following ADS scattering amplitude, okay, where G is the bulk amputated Green's function, while psi are some like smeared bulk to boundary propagators. So this is essentially a smeared ADS CFT ADS correlator, okay, and in the flat space limit, which is basically defined as you have very energetic wave packets. You can show that like this bulk to boundary propagator that becomes some sort of a plane wave thing, and you can replace the amputated bulk Green's functions by the flat Fourier transform of the flat space Green's function. Okay, and using this together, like I mean, they showed that the flat space S matrix of a D plus one dimensional QFT, you can get from a D dimensional CFT correlator in the from the bulk point. Okay, the bulk point limit of the ADS, the CFT correlator. And more precisely, what you should just take away from this is that like the coefficient of the rho or tau singularity of the bulk point correlator, that's just the S matrix, flat space S matrix. You can show that, okay? And I mean, you can naturally reverse this formula to get like, you know, a bulk point correlator, the CFT correlator in the bulk point limit as an integral over your flat space S matrix, okay? All right. So what happens when we take, for example, like the sigma goes to 0 limit also of the bulk point correlator? We will see that basically translates to Regge limit of flat space scattering amplitudes. Okay, so it's important that the Regge limit has straddles both the causal regimes. You can take the Regge limit on both the causally Regge sheet as well as the causally scattering sheet. Okay. Now let me just take a this thing that like what we have learned so far. We have studied two Lorentzian regimes. We have studied two kinematic regimes of interest. In one of them, we note that like we have chaos bound constraining the correlator. The other one, we saw that it is relevant for flat space scattering. And now we have to put them together, like to get our bounds. Okay, so what we want to do is that like we want to take the Regge correlator, and then we want to analytically continue to a different Lorentzian configuration. Okay, check how the sigma scaling behaves on the other sheet, and how the rho singularity comes about in the other sheet. Okay, and hopefully, I mean, that's what we are going to do now, and we will then eventually relate the chaos bound to the growth of the S matrix.
Subham, maybe 5 more minutes, I think.
Oh, I'm just starting, like, so like.
Just start to wrap up.
So yeah, so like just to be like more precise, what we focus on in our work is that we are looking at bulk contact terms for scalars, photons, and gravitons, and this is the ADS correlator for such a thing, and we study the Regge limit of this correlator. Okay, I won't go into the details since I don't have time, but what we can show more formally is that like this Regge correlator can be expanded in a power series form like this, where Hn is some analytic function of A and the polarization vectors. Okay, and what the most interesting thing about this thing was that we found is that for the particular class of contact terms that we are looking at, this theta scaling, this decouples from this guy. Okay, this is a complicated integral over like some hyperbolic manifold. Okay, but this theta scaling kind of decouples from it. Okay, and
what was theta again? Well, sorry, maybe I lost the thread. Theta is the scattering angle or something?
Yeah, it will turn out to be the scattering angle. Yeah. So what we see, the upshot of this is that, like, the analytic continuation from one causal regime to the other causal regime was that you tune A, this object A, which was basically tau by theta, from A greater than 1 to A less than 1. And since this theta scaling like decouples from this complicated integral, we were able to, like, go from one sheet to the other very easily. And this is because of the simple nature of the conformal integrals for bulk contact correlators. Okay, so basically, like, what we found is that, like, schematically, like, if you are studying Regge correlator in one Lorentzian regime, you can analytically continue to the other regime without affecting the power of the exponent of sigma in the analysis. Okay, so and like now that we are in causally scattering regime, what we can do is that we can take A goes to 0 limit also, which is corresponding to the bulk point limit. Okay. So let me just skip this. So the entire analysis of what I just said is that, like, in the limit that you take first theta goes to 0, do an analytic continuation, and then take A goes to 0, your Regge correlator behaves like this. So I'm being very schematic, but like we have checked it for a large class of contact diagrams with polarizations and all, like this thing, it behaves like this. Okay. The interesting part is that the crucial thing is that, like, as you do an analytic continuation, the exponent of theta or sigma doesn't change. Theta is basically like sigma is basically theta squared. So, like, I mean, sigma and theta, they are the same. So this does not change. Okay. And so therefore, like, as you can see, like from like already you can see that, like, you have bounds on one part of your correlator in a particular causal regime. You analytically continue and it does not change. The exponent does not change. So that bound continues to hold, right? I mean, this thing. So there is no, like, in the sense that what we were afraid of is that, like, whether the exponent of sigma is enhanced or, that possibility was ruled out by explicit analysis of these integrals. If it were increased, for example, like if the sigma powers increased, then that would have been a problem, because something which is allowed by chaos bound will not be allowed by CRG. Right. I mean, see, so that sort of a thing, like we tried to avoid. We showed that for the specific type of correlators we are looking at, it's not possible. Okay. So now, now I'll just do this. I will just go to this thing. So basically, like I just skipped over the other section, but you can take. You have basically, we are looking at the holographic correlators in two orders of limits. Okay, one is that theta goes to 0 first, and then tau goes to 0, and then the other limit is you switch it around. I mean, this is the same as like sigma goes to 0 and then rho goes to 0 limit. Okay. Now, what we show is that, like, what we have carefully checked is that, like, you know, in this region we have this, and in the other limit we have this. Okay, and we had shown that indeed, like, this is the leading part of this expansion, but the subleading parts behave like this. Okay, but these are polynomials of sigma and rho. So, like, the subleading guys are such that, like, you know, they are indeed like the sigma and rho powers both decrease. It's not like the sigma power is decreasing and rho power is increasing or something like that. Okay, that is very important. And one can show, like, one can argue that this a prime is always greater than equal to a. Okay, because of this double power series expansion. Okay, so all right, and so what we have shown is that, like, for a specific class of bulk contact terms, sigma goes to 0, the rho fixed, the correlator scales as this, and in the other limit, and by taking rho goes to 0 first, we have shown that it behaves like this with the power exponent a, where a prime is greater than a. That is like some details that I didn't have time to explain it to you, but and therefore the chaos bound therefore implies that this that a prime must be less than 2, and therefore a must be also less than 2. And this sigma to the power a, that basically comes from, like, a flat space S matrix which grows like S to the power a in the Regge limit. Okay, so if you have a S matrix, so therefore, like, the fact that this implies that you must have S square less than equal to 2, a flat space S matrix less than equal to 2. Okay, so yeah, that's the main result. But yeah, of course, like, we have shown it for holographic CFTs and also for very particular type of contact interactions, like, I mean, just contact interactions. We are trying to figure out if similar things hold for, like, the exchange diagrams or even loops in the bulk, maybe. Okay, but as of now, like, we have some technical problem regarding interpreting the exchange diagrams, like how to think about flat space scattering coming from exchange diagrams in the bulk. We don't find any localization as such, like, you know. So yeah, so let me just point out, like, what we did, like, you know. So we considered a large N CFT with a local bulk dual. That means you're considering local contact terms. Now, if the contact term interactions grow faster than S square, therefore the corresponding CFT correlator violates the chaos bound. So therefore, like, we put some bounds on the growth of the contact term interaction in flat space. Okay. The key feature which helped us really was the fact that in the ADS correlator, the coefficient of sigma did not change when we were analytically continuing from one causal region to the other causal region in the correlation function. Okay, and this leads us to think, like, I mean, what sort of non-trivial interaction structure between sigma and rho could there be such that it fails? My impression is that like even for exchange and loops, this will like at least for one loop diagrams in the bulk, like this probably will go through. There are results in literature which show that like the sigma power can decouple from the rest of the integral, and it doesn't care which Lorentzian regime you're in, as long as
I don't understand. If you start doing loops, won't you face the fact that it's not reasonable to truncate to a finite derivative order?
Sure. I'm saying that like as an algebraic exercise, just not like, you know, how like the thing, what it seemed, okay. So
but the loop diagrams at a fixed derivative order are not finite and are impossible to renormalize at a fixed derivative order. Like the exercise does not make sense, I don't think.
We are just wanting to like see if sure, like I mean, okay, yeah, maybe not loops, like in the sense that like so let me put it this way, like if I want to say study loops, that would imply that I am trying to see how corrections to 1/n corrections to chaos bound come about. 1/, like further corrections to chaos bound come about. Does that like, indeed, it's not clear that whether, I mean, considering an ADS loop, whether it makes a sensible, whether you can get a sensible flat space limit like of ADS loops.
But do we expect, just in the context of the chaos bound, that the 1/n corrections will modify the leading high energy behavior of the amplitude? I would have thought the answer is no.
No. It's not like so
so in what sense would they modify the bound? The bound
right. So the finite in chaos bound, just from CFT principles, is that like the correlator should just grow as S, not S square. This basically comes about from the fact that like in the CFT correlator must just by unitarity must be like constrained by the normalized correlator must be constrained by 1, not okay. So what we want to see is that like how the successive, like, you know, corrections come about. Like, so the chaos bound as done by Mallasena and collaborators is at 1/n square. So you have something, the leading term, which is the normalization of the 2-point function, product of 2-point function, and then you have 1/n square with the growth. And then you, if you incorporate loops, you will have, if you probe further, like, you know, further subleading orders in 1/n, that correspond to, like, you know, loops in the bulk, right? 1/n to the power 4 or 1/n to the power 8. And the idea is that, like, as far as I remember, is that like the coefficient of that growth must be great. I mean, it must be bounded, but the bound is greater than 2. Like, it can grow faster than 2. But so subsequently, like, you know, you have like a you have a kind of a geometric series which sum up to give you a something finite. Like, that sort of an idea is there, I think. So that's why roughly, like, we wanted to see, like, if it can be, yeah, because these things are like, you know, that the S growth that I'm talking about is really like the full quantum bound, like from, like, if you believe the ADS safety, like the flat space limit business, like it's just that. And like, so of course, like, we don't know how this thing, so that's why we were thinking that maybe one loop diagrams we can try to see what will be. But yeah, it's not an efficient way of doing about it, because like you would need to sum and just like many, I mean, you have to sum up like infinite number of loops to get like, you know, whatever you want to get. Like it's non-perturbative result. Yeah. So and also like yeah. So that was the kind of motivation behind us studying loops. Like yeah. And also like the obvious, even before loops, we want to exchange it to we want to generalize it to exchange diagrams where I mean you want to show that like not only contact flat space S matrices, but like, you know, if you include pole exchanges, that also is bounded by S square, but that is a work in progress. And like I don't have anything definite to say about it. Also, like in this analysis, we were not able to treat massive external spinning particles. We just considered photons and like gravitons. And the reason is that this flat space limit, the way you take the flat space limit is that like you tune the energy of the particles that you are pumping in to be very large, so that like, you know, you have like you probe a very small region of at the center of radius, which you can approximately think it to be like flat. Now, since omega is greater than any scale in the theory, the kind of like, you know, the mass of the external spinning particles kind of gets washed out in this thing. But there have been like subsequent follow-ups of this formalism by Hijano and Komatsu, and I was trying to like see if their methods can be used to derive kind of a similar bound for massive external spinning particles as well. But yeah.
Just physically speaking, like if the Compton wavelength, like 1/m, is just much smaller than the ADS radius, isn't that enough? Like, won't it basically look like a flat space correlator?
Say that again. Sorry.
Don't you just need basically like the Compton wavelength of the particle to just be much smaller than LADS? Like, won't that give you some sort of flat space limit? I don't know. I'm not very familiar with these things, but I'm sort of surprised you need m to be 0.
Compton wavelength.
It's just like 1/m being like much smaller than LADS.
No, you need the m to be very sorry, getting confused. Compton wavelength, you mean?
It's fine. It's not very important.
No, I don't have an answer to that. I'm not. Yeah.
You scale the flat space limit, radius of the infinity limit, and you need to scale the mass also. Only the mass that survives in the end.
I see. Okay. Well, are there any more? Well, first we can thank the speaker. And if there are any more questions, or
There's more questions, we can go up to his office.
yeah. Any more questions from online or?
Nice talk. Thank you.
Okay, thanks, Subham again.